Hello everyone, welcome to the chemical engineering simulation where we are using DWSIM to simulate the chemical processes. Today we are going to discuss about the absorption column simulation. As in the previous videos, many of you asked to make the video on this, so I am uploading the video on this. So first we will understand when we use the absorption column. So as a first thing, you should always think of this as a choice to separate the mixtures, because it is gonna make your job easy sometimes. So this is one among the first choices. And second, when you see the distillation of that mixture is not going to give better results, or sometime it is possible but it is so inefficient that the cost is too high, or the process parameters are such that maintaining them in the plant environment is required very controlled setup. So in that scenarios you go for this. Or when we found that one of the component has a higher affinity toward one of the solvent and which can easily be separated from the component, then we go for this. And what happen in the absorption column, we add a solvent in the column, then the solvent had a affinity toward one of the component, that component is extracted by the solvent and dissolved in the solvent, and in this way it enables the separation. So in today's simulation, our objective is to learn how to simulate absorption column in DWSIM, optimize the flow rate to achieve the desired separation of the mixture of ammonia and air by the help of the solvent water. So the process parameter will be ammonia and air at a flow rate of 100 kg per hour, where the air mole fraction is 0.8, and absorption column with 12 number of stages. Then we have a water flow rate to start with 250 kg per hour, and then we are going to optimize it to achieve the desired separation. Why I choose this example? This is also very crucial because in the industry we use the water absorption techniques to remove ammonia from the air that we are going to discharge in the environment, so that we are not polluting it, or any other gas mixture we are washing down the ammonia from, or stripping the ammonia from the gases, so that ammonia is not released into the environment. This is how our flow sheet will look like. We will add water from the top because of its natural flow, or because of its density, it is gonna come down, and as air and ammonia are gases, they are gonna go upward, so we will add them from bottom. So it will be a counter flow in which water will come from top, gases are going from bottom to top, water is coming from top to bottom. They will go mix with each other, and they will get lot of time where water will extract ammonia from the gaseous mixture, and then air will come out. So this is how the flow sheet will look like. So let's go to the DWSIM, open the DWSIM, maximize the window, go to the new steady state simulation, then click on next, add search air in the search bar and add it by clicking on the checkbox, then add water, similar fashion, again search ammonia, added ammonia, click on next, use Ping Robinson as a thermodynamics package, click on next, use the C5 as system of unit, because most of the units that the knowledge that is available for process simulation to us is in those units only. Click on next, then finish. After that, go to the columns. From column, select the absorption or extraction column. Now what I will do, I will stop the immediate simulation for some time, because I am gonna arrange and name the flow sheets. So I will name this as a water. As of our I am gonna name this as a ammonia and air. I will click on enter, then I will go to 3, I will make it as a air, then I will click on 4, make it as a water plus ammonia. This is how our flow sheet actually look like, desired flow sheet. I think now next steps will be adding the flow rates. So for water, as I already know, it is 250 kg per hour. I will add it as a 250 kg. Compound amounts, here I will make it as a 0. ammonia is 0, I will say accept. So this whole flow stream will contain the water. Now you can see. Now next I will go to ammonia plus air, compound amounts. Here water will be 0, air will be 0.8, ammonia will be 0.2. I will say accept, it will accept it. Then I will make it as a 100 kg per hour as of the problem. Now next step is go to the absorber. Here I will go the absorber. It is not a liquid extractor, it is an absorber. Number of stages by default is 12. There is no condenser in this or top pressure. Top pressure will be normal at 1 bar, will be at the atmospheric pressure only. Then we will go to the column pressure. There is no column pressure drop. This we are not gonna touch because it is 0.5, which make this column a 5 meter long column, 6 meter long column. So it is okay to have a 6 meter long column. It is very natural, and other things we don't gonna touch now. This is specification. Now it stays. I come to the connection. This is a column feed. Product air and water plus ammonia. Duties, there is no duties. There is no side draws. Stream water feed. Water I will make at a top stage. Ammonia plus A and air from the bottom stage. Need to make it as a top stage. Click on enter. This is gonna save. Now go to the insert bar, add property table, insert property table. 3 property table we want, 1 2 3. Why I want 3? Let's see. What I will do, I will click on this. I will go to the ammonia and air. Here I want temperature, pressure, mass flow. Then I will go to the mass flow of mixture ammonia versus the whole mass flow mixture and ammonia. These are the parameters for me, no issue. I will double click here, air. Similarly I want temperature, pressure, mass flow, and mass flow of ammonia mass flow mixture and ammonia. Similarly here for water plus ammonia, temperature, pressure, mass flow, and I want, you will gonna get it sooner or later why I am adding this. And then I will add here mass flow. Now these things are in front of us. I will go here, remove this, click on solve. Okay, no issues. Let me check water. Flow rate is all okay, not an issue. Let me check this one, all okay, not an issue. Ammonia compound amounts I know. So and this one states are okay, not a big issue. I will see the warning. Click on this. I will go to general. What I will do, I will just make the flow rate of water a little bit higher. I will make it as a 300 kg. Let's see. Is it running? Yes, it is running. Here you can see I had added ammonia 12.8 and almost recovered the ammonia, because here the mass flow of ammonia is 12.8174. 300 kg is water, almost little bit of water goes stripped away with the air. So this is the best separation that I can achieve, what I will say, because mass flow I literally make it 0. But let's say I started with 260. Now you see, let's say I make water as 100 only. Just to explain how to do optimization in this case, I am taking the example, okay, 100 is not working, let's say 210 will work. No, 210 is not working. I will start with 251. because here we are using a different approach. What I will do to demonstrate it, I will make it as a 260 only. Okay, let's say run it. I am getting it. What I will do, I will not reduce the water flow rate, I will gonna increase it. Let's say the flow rate is become 150. Sorry, let's say it is 100 kg per hour. Same only. What I will do, I will make it more condensed with the. Give me a second, I just want to demonstrate. Now for this I required more water basically, so I will make water as 300. So now it will go to the 350. Converge very well. Ammonia is very soluble in water, so we are not able to get anything in between. If we are reducing water too much, then the column is dried of water, and then the temperature that we are gonna get in the solution is different. So now I will change this to this one. Now you see the solver is different, everything is fine. I make it as a 300. Yes, now you see I change the solver. Might be the problem with the solver, because it should solve ideally. In my consideration, it should solve. Now the problem that we had in front of us is to make water flow rate optimum so that we get the desired separation, but we are not wasting lot of water also, because water is also a valuable resource, and in industry we always minimize our water uses, because it's also so our commitment toward the environment. So it is taking time. Let me check. Okay, not an issue. I will say about. I will not go at it. I will go at 260 somewhere. Solve. I will say about, then click on solve. This part is take little bit of time, because of the when we really reduce the water amount, the calculation become very non-linear of kind, then the solver will take time. So for the just time being and to make it, let's say, make the point that I want to make, I am making water flow rate 280. Let him solve. Okay. I will wait for 30 seconds. Then I will gonna abort it and make it as a 300 only. This is to be aborted. Make it 300. It runs. Okay, let's say I want to 18% I am recovering too much, so let's say somehow I want to say, hypothetically I want to make it 0.00. I don't want to release little bit of ammonia also, So what I will do, I will go to the logical block, I will choose a control block, I will click on control block. I want manipulated object, that will be the water, manipulated property, water flow.